Okay, Assalamualaikum warahmatullahi wabarakatuh and very good morning to all. Hope you are doing well. Okay, so before I start my class today, please fill in the attendance form which I had given in your the WhatsApp group. Okay, please fill in the form, the attendance form. Okay, and also the link is given in the chat area. Okay, for those who didn't access the WhatsApp group, you can access the attendance form link at the chat box. Okay, I already put the link for the attendance form. Okay, so I think I shall start the class. So it will be the continuation of the previous lecture on the title of pressure and fluid statics. Okay. Okay, can you see my slides? 3-3. Okay, can everyone see it? Okay, so is my voice clear? Can you hear my voice?
Yes.
Yes.
Okay, thank you. Okay, so today I'm going to start with 3.3, Introduction to Fluid Statics. Okay, so what does fluid statics mean? If you remember the first lecture, I have explained about some important terms. Okay, statics means something that doesn't move. Okay, doesn't move at all. So it's just in a motionless condition. Okay, so fluid statics, it deals with problems associated with fluids at rest. Okay, so it doesn't move. One good example is like water in a pond, okay, or in a container. So it doesn't move. As compared to water flowing in a river, it always moves. So that is not fluid static. Fluid static is any water that doesn't have any movement. Okay, one example is like water in the pond or in a lake. Okay, and please remember that fluid is not only considered for liquid. Okay, it can also be for gases. So a lot of people, when talking about fluid, they always think about liquid. Okay, but actually fluid can also be considered for gases. Okay, and then we have the hydrostatics term, which is when the fluid is liquid, and aerostatic when the fluid is gas. Okay, so normally this is the basic term. Hydro means water, aero mean gas. Okay, like if you heard about aerodynamic, meaning that's the flow of air, okay, towards some object. Okay, so there is a termination like aerodynamics, hydrodynamics, and so on. So hydro always refers to liquid, and aero always refer to gas. Okay, so in fluid statics, there is no relative motion. Okay, no movement of the liquid between adjacent fluid layers. Okay, between one part of the liquid to the other. Okay, and thus there are no shear stresses. Okay, shear stresses is caused by the movement. Okay, a force is being applied by that movement. Okay, since there is no movement for a hydrostatic fluid or liquid, so there will be no shear stresses. So the only stress for fluid static is the normal stress, which is the pressure, the P. Okay, So why is it important for fluid static? Because the design of many engineering systems, such as water dams and liquid storage tanks, requires the determination of the forces acting on the surfaces using fluid static. So basically, for people who are designing dams or storage area for liquid, they have to know what are the pressure developed inside within the dam or the storage. Okay, because pressure for liquid, okay, the deeper the liquid, the higher the pressure, because the higher the mass. Okay, so they have to think about the thickness. If they're going to design a very big storage tank, so what is the thickness of that storage tank should be? Otherwise, when we put a lot of liquid inside it, the container will have leakages, okay, because it cannot withstand the pressure being introduced into the container. Okay, so one thing is to know the pressure, the overall pressure inside the tank or the container, so that the engineers can calculate the thickness required for storage of that particular liquid. Okay, so one very good example is the dam. So normally the dam, the engineers will have a very thorough calculation on the thickness of the dam wall, okay, so that it can withstand the required level of water for the purpose of generating electricity. Okay, so moving on to 3.4, hydrostatic forces on submerged plane surfaces. Plane surfaces is something which is smooth. It's a straight, okay, straight surfaces. Because after this, we have something which is not plane surfaces, which is not straight surfaces, okay? So now I'm talking about hydrostatic forces on submerged plane surfaces or straight surfaces. Okay, if you see on the right hand side at the bottom part, so we can see a very straight like wall here. We have two A and B. So A is where the atmospheric pressure, normally is 101 kilopascal, is taken into consideration for the calculation, or sometimes calculation doesn't need to take the atmospheric pressure. Okay, so once again, for pressure with certain depth, the formula is P equals to rho GH. Okay, so we have to consider the density of the fluid or liquid, the gravitational force, which is always 9.81, and also the height. Okay, and also for hydrostatic force on plane surface, one important term is the centroid. Okay, centroid. What does centroid mean? Centroid mean is the center for that particular object. Okay, if you see here at the most bottom picture, there is the center of surface. It's really the center point for that particular object. If you see the ball arrow in the middle, okay, so if you see the left hand side and the right hand side, they are equal balance of 7 arrows. Okay, 7 arrows on the right hand side and 7 arrows on the left hand side. So centroid meaning the center point of that particular object. Okay, so is it important? Yes, it is important, because after this you will see why it is important, because it's going to be used inside the formula, okay, for hydrostatic force on plane surfaces. So centroid is the center of the surface of an object, okay, and this is how we can get the center, okay, or the center of an object. Okay, we can simply to go directly to the center, or if for a very complicated object, then we have to use formula. Okay, all these are examples of where centered position is. Like for square, circle is very simple because it's very, they have very same angle. Okay, but like for this, it's quite difficult. So for EF, so we have to use formula. Okay, so center once again is the center position of an object. Okay, and the other important thing about hydrostatic force is the pressure prism. Okay, if you see the diagram here, it forms a prism. Prism means is a formation where at one side of the formation is okay, the dimension is different. Okay, if you see starting at the top, the dimension there is narrow, but as it goes down deeper, the dimension is getting broader. Okay, it's longer as compared to near the surface. Okay, over there the length is narrow as compared to the length at the most bottom part, which is much longer. Okay, so why is this happening? Because as I mentioned before, the pressure with certain depth, the deeper the distance we go, the more pressure, because the more weight of the mass, okay, at that particular position. As an example, if you see at the surface, the first arrow, the whole volume over there, the mass of water over there is lesser than the volume of water at the most bottom part, okay, at the P, if you see, okay, surface and P. The volume of water is different because for P here, we have to take consideration all of the volume starting from the top until that particular position at P, okay? But for calculating the pressure for at surface or A, is only the mass at that particular area, which is at the top. So we don't consider all of the masses at different level. But for at the most bottom part, we have to take all of the masses. Okay, so that's why as we go deeper, let's say in a sea or a lake, the pressure is getting higher. Okay, so like one example is submarine. Every submarine has their own limitation. They cannot simply go any deeper. Okay, because the more deeper, the pressure will act on the submarine body. Okay, so if they go beyond the limitation, so the submarine will be damaged. Okay, so that's why we have a prism formation here, because the pressure is different from one depth to another. Depth at the top, the pressure is lesser than depth at the bottom. Okay, so that's why we have a prism. We don't have a rectangular. Rectangular means the pressure is all the same. Okay, but it's not for hydrostatic force in liquid. Okay, hope you understand. Okay, so this is one example, another pressure prism diagram. Okay, if you see, this one is much more clear. As we go deeper, there will be more pressure being developed. Okay, so that's why there is the length is different, starting from the top to the bottom. Okay, and you might be asking, what is the ball area, the big arrow? The big arrow is the average pressure. Okay, so you might be wondering, why is the average pressure is not in the middle? Okay, it's not in the middle of the object. Like centroid is the center position of an object, that is centroid. But for P average here, pressure average, if you see, it's not at the center. Why? Because we have to add all of the pressure determined from the top to the bottom, and then we divide it to get the average. Okay, so that's why it's not always to be in the middle. Okay, it will not always be in the middle because it's a, as I mentioned before, it's a pressure prism. Okay, So as we go down, the pressure value is higher. So if we take all of the pressure value and divide it by the depth location, okay, it will be not in the center, okay, because as we go deeper, the value of the pressure is higher. So that's why the big arrow or the ball arrow representing the P average or the pressure average is not at the center, okay, because relating to the pressure prism. Okay, so don't worry about that. But for centroid, the center position of an object, it should always be in the center. Okay, if it's not in the center, so there is something wrong, maybe with the calculation or something. But for average pressure, it doesn't need to be in the center. Okay. Okay, and for hydrostatic forces on plane or straight surfaces, the formula FR. So FR stand for resulting force. The force happen or the force obtained. Okay, resulting force or FR is equal to P0, P atmosphere above the lake or above the liquid, plus with the actual formula rho GH, but in this case, it's not height. Okay, it's different. Okay, so the H is defined as S. This is the surface above the plane object. Okay, S refers to the height above the plane object. Okay, that is the S here. And B divided 2 is the center or the centroid. Okay, the center position of an object. We don't take B. Okay, in the formula is center position of the object or centroid. Okay, so if you have to use the formula, if you put B, so you get wrong answer. For hydrostatic forces, formula, the H equation is S plus B divided by 2. Okay, that is the equation. And if you see here, it times with A and B. Okay, B refers to here, the total height of the plane object, okay, or the straight object. A here is referring to the thickness, okay, the thickness of the plane object. So normally, people don't take consideration the thickness, okay. So since thickness is not taken into consideration, the AB term is not included in the formula, okay. In some example, after this you will see some example. So since thickness of the plane object is not taken into consideration, so the formula after this formula will not have AB after PO plus rho GS plus B divided by 2. Okay, and to make things easier, normally people will not take into consideration also the P atmosphere. Okay, the pressure on the top of the liquid. Okay, so we just left with FR equals to rho G in a bracket S plus B divided by 2. Okay, so this is one example. So maybe we'll be coming out for your test. Okay, so as I mentioned before, if you see, if we omit, we don't take into consideration the thickness. So AB will be disappeared, and also PO. So FR is just left with rho G S plus B divided by 2. Okay. So we will see one example. Hydrostatic force acting on the door of a submerged car. Okay, the question is, a heavy car plunges into a lake during an accident and lands at the bottom of the lake on its wheel. Okay, so this particular car, the picture on the right hand side, is at the bottom of the lake. Okay, the door is 1.2 meter high. The height of the door is 1.2 meter and 1 meter wide, and the top edge of the door is 8 meter below the free surface of the water. Okay, the height starting from the surface of the lake up to the top of the car is 8 meters. Okay, so the question asks, determine the hydrostatic force on the door and the location of the pressure center, and discuss if the driver can open the door. Okay, so the question asks about the hydrostatic force on the door. That is one thing. Location of the pressure center, and discuss if the driver can open the door or not. Okay, let's say there is a driver inside the car. Can he open the door of the car? If that situation happens, okay, we have to determine the pressure. How much is the pressure? More than 8 meters below the lake. Okay, so the solution: a car is submerged in water. The hydrostatic force on the door is to determine, and the likelihood of the driver opening the door is to be assessed. Okay, so once again, hydrostatic force is also pressure. Okay, so maybe you are confusing. Is hydrostatic pressure is the same with pressure or not? Actually, it's the same, but for something that is inside the water, for determining the pressure, we known as hydrostatic force. Okay, so assumptions that can be done: one, the bottom surface of the lake is horizontal. The passenger cabin is well sealed so that no water leaks inside. Number three, the door can be approximated as a vertical rectangular plate. The pressure in the passenger cabin remains at atmospheric value since there is no water leaking and thus no compression of the air inside. Therefore, atmospheric pressure cancels out in the calculation since it acts on both sides of the door. The weight of the car is larger than the buoyant force acting on it. Okay, so properties: the average pressure on the door. Properties: we take the density of lake water to be 1,000 kilogram per meter cubic throughout. Analysis: the average pressure on the door is the pressure value at the centroid midpoint of the door and is determined to be, okay, as I mentioned before, here, FR equals to rho GS plus B over 2, okay, the simplified equation. So the pressure, so the question asks about the pressure at the door. Okay, so to calculate the pressure is simply use from the original formula, which is P equals to rho GH, now becomes rho G times Vs plus B divided by 2. Okay, so by using that formula and then key in what value that we have given. Okay, so we have the density, which is 1,000 kilogram per meter cubic. Gravitational force is always 9.81 meter per second square. Okay, so this part you must be really careful. Okay, because sometimes you just simply put B. Actually, is the center of that particular plane surface. Okay, it should be divided by 2. Okay, so sometimes maybe overconfidence, someone will just put B. Okay, but actually you will get wrong answer. So it should be B divided by 2. So the S is the surface, is the from the top of the object to the surface of the liquid, which is 8 meters. So that is the S. B is the length of the door or the plane surface, which is 1.2 meter. So it should be divided by 2. And then we get 84.4 kilonewton per meter square. So that is the force, or that is the pressure, okay, at that door at that particular depth. Okay, so we have solved for one part of the question. Okay, any questions that anyone has? Are you clear on this? Okay, so whatever is, you must always remember the pressure formula. Okay, we also have P equals to F divided by A, force by area, and then we have P equals to rho GH. And now when talking about hydrostatic force for something that is inside a water or liquid, the formula is P equals to rho G S plus B over 2. Okay, so I hope you can really memorize this formula, because it will be useful for you later on when you are doing other subjects, and also maybe when you are working later on. Okay, so these are the formula that you must remember in your heart. Okay. Okay, and the second part is, okay, actually the first part is not complete yet. Okay, so the actual resulting force is P average times with the area. Okay, the area of the door is the height is 1.2 and the width is 1. So that the area is 1 times 1.2. Okay, so the actual force is 101.3 kilonewton. Okay, if you see here is the actual pressure, but for actual force, when we're taking into consideration the area, the force is 101.3 kilonewton. Okay, and the last part of the question is asking whether the driver can open the door. The second one is the location of the pressure center. Okay, what is the location of the center pressure? So we have a height of 8 meters on top of the, starting from the top of the car to the surface of the lake, and we have the height of the door for the car is 1.2 meters. So what is the center location? Okay, location of the pressure center. Okay, so we can use this formula, which is not shown earlier. Center of pressure equals to S plus B plus 2 plus B square divided by 12 times with S plus B divided by 2. Okay, you get 8.61. Okay, but basically, to make easier, you just divided 1.2 divided by 2, and then add to whatever value for the surface. Okay, the surface height, the top of the object to the surface of the lake. Okay, so that is an easier calculation. So whatever the height of the object, the plane object, divided by 2, and then add to the height of the surface. So if you if the door is 1.2 meter divided by 2, we will get 0.6. So 0.6 plus with 8, we will get 8.6. Okay, if you see, is very similar with this. Either we can use this formula, or we can use we can directly use 1.2 divided by 2 and then plus 8, which is also 8.6. Okay, please remember, for the location of the pressure center is not here. Okay, because it takes the total height. If you just say 0.6 is the location of the pressure center, is wrong, because location of the pressure center means all of the pressure. Okay, it's not just here. If just there 1.2 meter, meaning that the car is only 1.2 meter below the lake. That is right if it's 0.6. Okay, if you answer 0.6, it's right if the car is only 1.2 meter below the lake. But if the car is in this situation, more than 8 meter, if you answer 0.6, it's wrong. Okay, so the other easy way to answer the location of the pressure center is simply the height of the plane object divided by 2 and plus the surface height. Okay, of the plane object to the surface of the lake. Okay, so in this question, we should get 8.61. Okay, so discussion. Can the man open the door if that situation happened and the man is trapped inside the car? Can he open the car doors? Okay, by thinking of the pressure being developed outside of the car. The pressure developed outside the car is 101. If we take into consideration the average, or if we just take the pressure is 84.4. Okay, so the discussion is that a strong person can lift 100 kilogram, which is a weight of 981 Newton or about 1 kilonewton. Okay, a very strong person can only open or push something that is only about 1 kilonewton. But in that situation where his car is 8 meters below the lake and the pressure develops is 84.4 kilonewton, or 101.3 kilonewton, which is more than 1 kilonewton. So it means that he cannot open the door. So one thing he can do is try to open the window a little bit so the water can enter. Okay, so when the water enters slowly into the car, so the pressure will be different because there will be pressure outside coming in from the outside of the car, and also the pressure coming out from inside the car. So pressure difference making the total pressure is lesser, so he can open the car doors. Okay. Okay, so
maaf sir, saya tu formula mana dapatnya yang
mana?
from moot point YP.
Okay, for yang this one inside the textbook. Okay, kalau siapa ada textbook.
Okay, thank you sir.
Okay, okay. Okay, so kalau my explanation just one time, if you still unclear, you can have a look back. Okay, so read again the question, and then you don't understand, you can ask me maybe in the WhatsApp group. Okay, because sometimes it's very difficult, even for one example, to be understood. Okay, so basically just I'm showing you how to use the formula. Okay, so 3.4, I'm talking about hydrostatic forces or the pressure on plane or straight surfaces. For 3.5, it's also the same thing, hydrostatic forces, but on submerged curved surfaces. Okay, it's not straight. The surface is not straight. Curve meaning it has some edges. Okay, some bends. Okay, if you see this one example is like the body of a ship. It's always like this. Okay, it's a curve. Okay, there is a purpose why the body of a ship is in a curved shape. Okay, it's not like a boxy or straight plane. Okay, because the pressure will act differently on curved surfaces. Okay, so if you see here, the force acting on the curved surfaces are much more complicated, okay, as compared to plane or straight surfaces. Okay, so I'm not going to talk about that. Also, the formula is quite complicated. Okay, so for your knowledge, if a question comes up, it will be on plane surfaces, okay, straight surfaces, not on curved surfaces. Okay, so actual dam, the surfaces is not flat. Okay, most of the time is curved surfaces. Okay, so in many structures of practical application, the submerged surfaces are not flat, but curved as here in Glen Canyon Dam in Utah, Arizona. Okay, why is it curved? Because the distribution of the pressure is lesser than on a straight surface. Okay, so that's why a dam is normally constructed in a curved formation. Okay, because the pressure distribution or the pressure acting on the surface is lesser than pressure acting on plane or straight surfaces. Okay? And that's why the ship always float, because they have a curved design. Okay, meaning that lesser pressure acting on that curved design. Okay, here is what happened to the pressure in a multi-layer fluid, okay, or different densities for a plane surface, a straight surface. Okay, let's say we have two different fluid. One is oil and one is water. Okay, so we have to know the density of each respective fluid, because density also will play a significant role on the force. Okay, if you see here, the force of water is higher than the force generated by oil. Okay, because of density. Oil is less dense than water. The higher the density, the more pressure will be developed, or the more force will develop. Okay, and that's why oil will float on water, because it is less dense than water. Okay, the more dense or the more heavy object, it will sink to the bottom. Okay, so if we have oil and water, oil will always be on top of water, because its density is lesser than water. Okay, if you see here, water, because of water density is higher, more forces is being developed below the oil layer. Okay, you see the force acting on the plane surface is lesser as compared to water. Okay, so this is going to be the last part, 3.6, buoyancy and stability. So what does buoyant force mean? Buoyant force means the upward force a fluid exerts on a body immersed in it. Okay, the buoyant force is caused by the increase of pressure with depth in a fluid. Let's say if there is an object on the surface of a liquid. Okay, whenever an object touches the surface of a liquid, there will be a force from the liquid which will try to resist the object from entering or sinking into the fluid. Okay, so that's what buoyant force means, the upward force. So the force within the liquid, it will try to resist an object from sinking into that liquid. Okay, but it will depend on several factors. Okay, if you see here, the buoyant force acting on the plate is equal to the weight of the liquid displacing by the plate. Okay, it will depend on the weight of the object, the density of the object, and the surface area of the object. Okay, so one very simple example is the weight. This is the very important thing. So the more heavier the weight, the upward force of the liquid cannot withstand. Okay, because it has certain limits. Let's say if we put a solid rock, which is 5 kilograms, we put on the surface of the water, for sure that rock will sink into the water. Okay, because the weight is higher than what is the upward force of the liquid. Okay, the upward force of the liquid cannot resist the weight of that rock, which is 5 kilograms. Okay, so maybe if the rock is very light, like maybe 5 milligram, so the upward force can make the rock float. Okay, and also maybe a rod of steel and a feather. So feather is very light, it can float, but steel is very solid and heavy, so it will float. It will sink into the water. And talk about density. Uh, oil and water, oil will be floating on water because the density is less. But if water and mercury is higher, is denser. Okay, the density of mercury is higher because density of mercury is 30,000 kilogram per meter cubic. Okay, so it's higher than density of water, which is 1,000 kilogram per meter cubic. So that's why if we have mercury and we pour into water, H2O, mercury will sink inside the water because the density of mercury is heavier than density of water. Okay, and surface area. We're talking about surface area. Let's say if we are swimming, we just put everything, our feet, our hands straight, okay, near to our body, we will sink because our surface area, the ratio of weight to surface area is higher. Okay, because our surface area is smaller. If we just put our hand and our feet are closing, okay, our feet are closed and our hands are next to our body. But if we spread our legs and spread our hands, it will increase the surface area. That's why if people do that, that people will float on the water. Okay, so if we just if we don't increase the surface area, let's say if you are on water or on sea, so the best way to not be drowned is try to spread the legs and the feet, okay, as to increase the surface area. So the bigger the surface area, the more resistant of the upward force of the liquid will be. Okay. So this is one example. This in the term of density. Okay. So for the force, first ball here, if you see, is a floating body. Why is it floating? Because the density of that body is lesser than the density of the fluid. Okay, so that's why it's always will be floating. It will not sink. Okay, because the density of the floating body is lesser than density of the fluid. Okay, but if the density of the floating body or the density of the body is equal to density of the fluid, so it will be suspended. Okay, it will be inside the water because it has the same density. Okay, but if the density of that body is greater than density of the fluid, it will sink inside the fluid. Okay, are you clear on this in terms of density? Okay, anything lesser than the density of the fluid, it will float. Anything that is any density that is equal to density of fluid, it will suspended inside the fluid. Okay, and anything that is denser than the density of the fluid, it will sink to the bottom of the fluid. Okay, so this is quite important because people use this principle. Actually, it's known as Archimedes principles. Okay, if you see here, this is a very large container ship. Okay, so some people might be wondering, how can a large ship like this doesn't sink into the sea? Okay, so what is the actual mechanism that makes this ship float? Okay, so one important aspect for a large ship is that at the bottom part of the ship or the ship body is and hollow area or empty area. Okay. Okay, so there is nothing at the bottom part. Okay, it's a hollow area, which makes it less denser than the density of the water. That is one thing. And the other thing is surface area. Okay, the larger surface area, meaning that the more upward force is being introduced, okay, is being applied, because the more surface area, the more force is being affected, okay, by the liquid. Okay, so that's why bigger ship has bigger surface area. Okay, with the bottom part, which doesn't, which is hollow, nothing. Okay, just has air. Okay, and with the help of larger surface area, that's why a big ship can float on water. Let's say if the bottom part is total solid, there is no hollow or empty area, then the density of the boat is heavier than density of the water. Okay, so if that happen, then the boat or the ship will sink into the sea. Okay, so that's what happened to the Titanic ship. Okay, because the side of the ship crashed with iceberg, and then water coming inside into the empty area. So the boat, the Titanic ship become heavier. Okay, and finally it sank into the bottom of the sea. Okay, and also important aspect for a floating object is the gravitational force. Okay. Okay, if you see here, for the first one, stable, the force by the buoyant body or the liquid body is higher than the gravitational force acting to the water. Okay, so that's why that particular object can float. Okay, because the force of the liquid is higher than the force of the gravitational force of the object. Okay, so for B, neutrally stable, the gravitational force of the object and the buoyant force of the liquid is balanced. Okay, it is still stable, it can still float. But for unstable, the gravitational force of the liquid of the object is higher than the buoyant force of the liquid. So that's why that object will sink into the water or into the liquid. Okay, so this is a more clear example. If you see the boat situation, okay. So the first one, FB, the buoyant force of the liquid is higher than the gravitational force, okay, of the ship. So that's why it is floating, okay. But if you see here, the buoyant force is not so great, and gravitational force acting is higher, okay, than the buoyant force, the upward force acting by the water. So the boat is not balanced. And to make more matter worse, okay, the center position of the ship, if the gravitational force is getting higher and the buoyant force is getting lesser, and the center position of the ship is getting away from the center, so the ship will overturn and then sink. Okay, so the position of the center of the boat is also important. Okay, so if this happen, let's say there is a leakage at the bottom part of the ship for the diagram number 2. If there are leakage, at the bottom empty part of the boat body, water coming in, but is not fully filled with water, and the boat is just a little bit off center, okay, from the meta center. The boat can still float and maybe can, if the port is not far, can reach the port. Okay, but if the water enters the empty area of the bottom part of the ship, but the center position of the ship is away from the meta center or the center position of the ship, so there is a tendency for the ship to overturn, okay, to be capsized, to turn 180 degrees. Okay, so that's why certain boats, they have balancer. Okay, if something happen like this, they will put more weight. Okay, if you see on the second diagram, there is more weight on the right hand side. So if that happen, there will be certain masses added on the left hand side to balance the ship. Okay, so certain big ships, they have that balancer mechanism, okay, to balance the ship whenever the ship has that off position from the center of the ship. Okay, otherwise slowly the ship will overturn, and then the ship will lastly sink into the water. So that's all the summary for the last part of the lecture, pressure and fluid statics. Okay, so I have covered pressure measurement devices, introduction to fluid statics, hydrostatic forces on submerged plane surfaces. Okay, so this part is very important. Remember back the example, okay, the formula. Hydrostatic forces on submerged surfaces. This one I will not touch on the equation and so on. Okay, and buoyancy and stability. So what makes a big ship can float, and how to make sure the ship is stable, okay, on the water. Okay, anything you want to ask? Okay, for your quiz and test, most probably I will do after the midterm. Okay, and just that assignment, maybe I give you the week before your midterm break. Okay, assignment. So maybe you have 3 weeks to do your assignment, and then you have to submit. Okay, but for your quiz and your test, I think most probably I will do it after your midterm break. Okay, so actually we are left with 1 more week, but there are 2 lectures to cover. So I see if I can finish it by next week. Okay, so then we don't have additional class. So I try my best to finish everything by next week, because after midterm break, Dr. Rahima will take over the lectures. Okay, so any questions? Okay, so my advice to you, please look back at the example that I given just now. Okay, the car inside the lake. Okay, and please look at the formula. Okay, anything else? Okay, please don't forget to fill in the attendance form. Okay, if no questions, I will see you next week. And once again, I will give you the summary, the simplified summary, okay, to make things easier for you, to understand, and also this recorded lecture classroom, okay, I will upload on YouTube. Okay, if no more questions, so thank you for joining my class this morning. I hope you all have a great day and take care of yourself. Be safe, okay? So see you next week. And all the best and good luck for whatever assignment you have, okay? I know you have integrated project that you have to submit this afternoon and other things, okay? So thank you and see you next week. Bye.